Good evening, ma'am.
Yeah, good evening, everyone.
Good evening.
Good evening, all. Let us start today's session. This week, actually, we started with the, you can all hear me, right?
Yeah.
Okay, the last week, we started the linear algebra, introduction to linear algebra, like vector space and subspace and so on. So, we will solve some problems related to that topic, okay? So, first let me share the screen. Is my screen visible? Is the screen visible? Okay. Okay, let's go to the first question. So, we already talked about the vector space in the class. So, here the question is, we have a vector space R3 and 4 sets given. So, among these, which one is a basis for the vector space R3? So, this is the question. So, here, okay, here the vector space is R3 over the field R. So we need to find what is the basis. Among this, which one is the basis? So what is the dimension of R3? Yeah. Excuse me. Yeah,
coordinates.
Yeah, can you tell once again?
3 coordinates will be there.
3 dimension. Yeah, dimension is a number, that is 3. Usually we write the basis of R3 as 1 0 0. That is, this is our standard basis 0 0 1. So this is our standard basis. Number of elements in this basis is 3. So we say the dimension is 3. Anyone is speaking? I am not able to hear. Okay, so here let us go to the first set A. So in these 4 options, we have 3 elements in each of the sets. So we just need to check whether the set is linearly independent or whether it spans the whole space R3. So it is easy to check the linear independence, that is whether the 3 elements in each set is linearly independent. If it is linearly independent, then clearly it is having 3 elements, means it is a basis for R3. Okay, let us go to A, first option A. So what do you think, whether A is a basis or not? Okay, is this A is a basis or not? Not a basis. Okay. Yes. Yeah, this is not a basis.
First is not a basis.
Yeah, give me 1 minute. Okay. Yeah, here this A is not a basis because the element 0 is an element in A, right? This 0 is an element in A, we can write, if I am writing this element, suppose 1 into 0, 0, 0 plus 0 into 5, 0, 0 plus 0 into 0, 5, 0. This is equal to 0, 0, 0. That is, I am writing these three elements, the linear combination of these three elements like this, with one of the coefficient as non-zero. So, this expression says that this set A is linearly dependent. Okay, is this clear for everyone?
Yes, sir.
Yeah, who is speaking? Actually, your voice is not clear for me. Anyone is having doubt in this? This is not a basis. First one. Anyone is having doubt?
No, madam.
Can you please repeat? Can you please repeat once?
Okay, I'll repeat. So we have given this set A. A is set 0, 0, 0, 5, 0, 0, 0, 5, 0. This is having three elements. We know that the basis of R3 is having three elements. We already know that. If we are able to prove that this is either linearly independent or this spans R3, then we can say this is a basis. So we are checking the condition whether it is linearly independent or linearly dependent. So this set, actually here I am having one 0, 0, 0. So I can multiply this 0, 0 with any scalar. I am taking a non-zero scalar. Okay. This non-zero scalar I am taking. For other two elements, I am multiplying with the scalar 0. So what I am getting is, if I am taking the sum, finally I will get the 0, 0. Okay. I am adding these three elements. So I am getting 0, 0, 0. So here this expression means I have written this linear combination of these three elements with one of the coefficient. This element, first coefficient is non-zero. Okay. The condition for linear dependent means three elements or whatever the n number of elements, if we are able to write it in a linear combination with at least one of the CA is non-zero, then we will say it is linearly dependent. So here in the expression we have one non-zero coefficient. This is 1. Okay. So this condition says that A is linearly dependent. That is, it is not a independent set. The first set is not a independent set. So for the condition to be basis is the set should be linearly independent. The condition is false here because it is linearly dependent. So it cannot be a basis. Okay, is that clear now?
Yeah.
Yeah. Okay. Actually, if we are taking any set, means any vector space and any subset, if 0 belongs to some S is any set, and if 0 means 0 vector belongs to S, then S is not linearly independent. Because this is the same reasoning, because if we are having 0 in the set, we can take the linear combination as some non-zero scalar, that is we can take 1 into 0 plus 0 into S1 plus 0 into S2 etc. plus 0 into Sn, where S1, S2 etc. Sn are all elements of S. Because these are all 0 means this sum will be 0. 1 into 0 means 0. So this total summation will be the 0 vector. So we will get a linear combination with at least one coefficient non-zero. That means this set S is linearly dependent. So what I am saying is, if any set contains the 0 vector, then the set cannot be linearly independent. Okay, is that clear? Now let us go to the next one. We already discussed the first option. So what do you think, whether B is a basis or B is a linearly independent set or not?
Linearly independent.
Yeah, linearly. Let us check the condition. Here B is the set 2 0 0, 2 2 0, 2 2 2. Okay. For that, to check the linearly independent condition, what we will write is C1 into 2 0 0 plus C2 2 2 0 plus C3 2 2 2. This should be equal to 0. 0 means the 0 vector 0 0 0 in R3, because we are considering in R3. So this condition we can write 2C1. So first coordinate, we will equate the first coordinate 2C1 plus 2C2 plus 2C3 equals 0. Next 0C1 plus 2C2 plus 2C3 equals 0, and the third coordinate is 0C1, 0C2, 2C3. 2C3 equals 0. We are just adding and equating the coordinates. From this condition we will get C3 equals 0. So C3 equal to 0. So C3 equal to 0 in the second equation. What we will get 2C2 plus 0 equal to 0. This implies C2 equal to 0. So we got C3 and C2 are 0. Both C3 and C2 0 means in the first equation we will get C1 equal to 0. Okay. So if we are writing it as the linear combination and if we are equating it to 0, what we are getting is both the coefficient C1, C2, means all the coefficient C1, C2, C3 are 0. That implies B is linearly independent. Hence B is a basis. Because we got a linearly independent set which contains 3 elements. So dimension cannot be greater than 3, of course, because it is R3. So B is our basis. Is this clear? Is the second option clear for everyone?
Yes, ma'am.
Okay. Otherwise, you can also check if you are taking any arbitrary element in R3. You can check whether it can be written as the linear combination of these 3 elements. That is also a simple exercise. You can just do that if you want. And what about the third condition? Is this a
Linearly dependent, ma'am.
Yeah, linearly dependent. From the set we can easily see this 4 4 4 is a multiple of 2 2 2 2. That means we can write 4 4 4 equal to 2 into 2 2 2, or we can write 8 8 8 as this 8 8 8 also an element of the set C. Okay, 8 8 8 as 4 into 2 2 2. So we cannot say this is, that means what this means is 4 4 4 minus 2 times 2 2 2 equals 0 0 0. That is, we have written it as the linear combination of elements of C with the non-zero coefficient. This minus 2 is non-zero, here 1 is also non-zero. So C is linearly dependent. So it cannot be a basis. Now let us see the fourth one. This is the fourth one. Okay. What do you think, D? Linearly dependent or independent?
Linearly independent.
Independent. Are you sure?
They are dependent.
The determinant is not equal to 0.
Okay. So let us see. D is the set 550 500 050. Okay. Now I am writing this as 550 equals 500 plus 050. Okay. Now what do you think, whether it is linearly dependent or independent? Or otherwise, as you said, you can check the determinant. Excuse me. Okay, we can check the determinant also. This is 550 500 050. See, the third column is 0, so of course this determinant is 0. Or from this we can write this is 550 minus 500 minus 050 equals the 0 element, right? That means we have written the 3 elements as the linear combination, so that its sum is 0 0 0 and its coefficient is non-zero. Here it is 1, here it is minus 1, here it is minus 1. So is the D is linearly independent? No, it is a linearly dependent set. Is this clear? Is the last option clear? Anyone is having doubt? Any doubt? Am I audible?
Yes, you are.
Yeah, okay. So let us go to the next problem. If you are having no doubt, let us go to the next problem. Okay. Here the question is, we have given one subspace of R2. The subspace, let us write it as S. S equal to set of all xy in R2 such that x plus y equal to 0. This is a subspace of R2 over R. So the question is the dimension of the subspace S. Okay. First of all, let us just verify whether S is a subspace or not. Is S is non-empty? Can anyone say any element, any simple element in S?
One minus one.
Yeah, 1 minus 1 belongs to S. Because 1 plus minus 1 is 0, this condition is satisfied. So S is a non-empty set. So to check the subspace condition, we know that if we are taking two elements in S, x1, y1 and x2, y2 in S, we need that x1, y1 plus x2, y2 should belongs to S. So x1, y1 plus x2, y2 means just a coordinate wise addition, x1 plus x2, y1 plus y2. Is this belongs to S? Is the element x1 plus x2, y1 plus y2 belongs to S? In order for an element to be in S, what we need to check is the two coordinates x and y, the summation of this should be 0. Here we have two coordinate x1 plus x2, second coordinate is y1 plus y2. So we just need to confirm whether these two, sum of these two equal to 0 or not. Let us see that x1 plus x2 plus y1 plus y2. This is equals x1 plus y1 plus x2 plus y2. Is this equal to 0?
Yes, ma'am, 0.
Yeah, because x1, y1, x2, y2 belongs to S. So this belongs to S. In the same way, if we are just considering a scalar and C x1, x2, this is C x1, C x2. This also belongs to S because C x1 plus C x2 equals 0. Okay. So we just verified that S is a subspace. Now we need to find the dimension of subspace. Okay, what we got is S is a subspace of R2. Okay, before going to find the exact dimension of S, let us see what are all the possible dimension of S. Okay, can anyone say what are all the possible dimensions? We know that S is a subspace of R2 and R2 is having dimension 2. Okay.
0, 1, 2.
Yeah, 0, 1, 2. It cannot be more than 2 because it is a subspace of R2. So, is dimension S is 0? What do you think? Can it be 0? Okay, when will be the dimension of a set will be a subspace will be 0?
Ma'am, some trivial solutions.
Yeah, trivial, because like say set to 0. Set to 0 means it is the trivial subspace of a vector space. In this case only we can say dimension is 0. Okay. If there is a non-zero element, of course the dimension will not be 0. So here in the S we already have 1 minus 1 belongs to S, right? So the dimension of S is not equal to 0 because there is a non-trivial element. Non-trivial element means at least one element will be in the basis and at least one non-trivial element will be the basis. So dimension S cannot be 0. Now the next question is dimension S is 2? What do you think? Dimension S, whether it can be 2 or not?
Ma'am, in that case, infinite solution or something.
Okay, see what is S? S is a subset of R2 and we know that dimension of R2 is 2. Okay, that is the maximum possibility is 2. If I am saying dimension of S is also 2, what we can conclude? S is same as R2, right? Is that clear?
Yes, ma'am.
Yeah. If dimension of S is 2, then S equal to R2. In our case, what do you think? Is our S R2 or not? Is S equal to R2 here? Okay, our S is set of all x, y such that x plus y equal to 0, right? R2 means set of all elements x, y and S is set of all x, y with the x plus y equal to 0.
Not equal to R square.
Yeah. S not equal
Yes,
to
ma'am, not equal to R.
R square because
yeah, not
for
equal.
S, it must satisfy that condition x plus y equal to 0.
Yeah.
R square is not good.
Yes. For example, if I am taking an element 1, 2 in R2, 1 plus 2 is not equal to 0. So it does not satisfy this condition. So 1, 2 does not belongs to S. Okay. So S is not equal to R2. S is a proper subspace of R2. So we have 3 possibility for dimension of S, that is 0, 1 and 2. We discarded the possibility 0 and 2. So the dimension of S is 1. Okay. Is this okay? Or explicitly we can, so this is not an easy, we cannot approach by this way always if the set is a bigger set, if the vector space is a bigger space. So let us see, S is set of all x, y such that this is an alternate method for finding the dimension, x plus y equal to 0. So from this condition we will see x plus y equal to 0 means x equals minus y. Okay. So we need to find the elements x, y, so that this condition x equal to minus y is satisfied. That means if we are having one particular element x, then y is already determined by x, that is y should be minus of x. Or if we are having the y value, we should be having x as minus of y. That is, there is only one variable which determines this both coordinate. That is, we can write S equal to set of all x, y is the minus x, negative of x, x minus x such that x is in R. Okay. From this also we can say, if I am taking a b equals 1 minus 1. What do you think about span B? Yeah, span B is the S. Okay, and this is only one element, that is a non-zero element. So B is also linearly independent, right? So we got a basis, that is a linearly independent set which span our S. So we know that dimension of S is the number of elements in the basis P. Number of element is 1. So in this way also we can say the dimension of S is 1. Is this clear?
Ma'am,
Yeah.
how come number of element in B is 1?
Yeah. Did you get why S is like this, x minus x? Up to this, is this clear?
Yeah.
Yeah.
Yes, ma'am, I got that.
Yeah. From this, like you can take either B as 1 minus 1 or 2 minus 2, any element you can take. Just for simplicity I am taking 1 minus 1. Okay. That means if I am having any element, say if I am having an element in S, suppose if I am having an element A minus A in S, what I want is this A minus A, I should write it as the linear combination of element of B, then only I can say B is a basis. So I am writing this A minus A as A into 1 minus 1, that is a linear combination of 1 minus 1. Okay. Or I can write it as A by 2 into 2 minus 2. This is also possible. Means I can take any element here, either 2 minus 2, this is also a basis, or I can take B3 as some 5 by 2 minus 5 by 2. Anything I can take. The only thing is it should span the element, span the set S. Span of B should be S, and only one element will be there. So it is linearly independent. Okay, is that clear?
Yes, ma'am, got it.
Yeah, okay. So we got the dimension is 1. So let us go to one general case. Suppose V is the vector space R2 over the field R. Now what are all the possible subspaces of for V? So for R2, what are all the possible subspaces? We know that the possible dimension are 0, 1, 2. So 0 is the dimension, means we already told that is the trivial subspace. So one subspace is our trivial subspace. Okay. Now the second case, we considered the 0 case. Then this case, last case is third case. This is our whole subspace R2. If the dimension is 2, the whole space R2. This is the subspace of R2. Okay. Now we have one more condition, this one. Okay. So we need to find all the subspaces having dimension 1. We already have one subspace, that is S equal to set of all x, y such that x plus y equal to 0. X plus y equal to 0 means x equal to minus y. Okay. That means set of all elements of the form x minus x. It means x minus x means this is our line. This is our line x plus y equal to 0. So the subspaces we considered here is the line, this line. This is having dimension 1, because if we are taking one element here, we are just multiplying or adding. Whatever doing, the element will lie on the same line again. So that is why this is a subspace. Okay. In the same way, we can see any line. If I am taking any line which passes through the origin, it should pass through the origin, because 0 should belongs to the subspace always. So if I am considering any line which passes through the origin, then it will also be a subspace. So that subspaces, that means all the such lines are the subspaces of dimension 1. So here lines passing through origin. That means in R2 we have 3 kind of subspaces. One is our trivial subspaces, and the second one is the line passing through the origin, that is any line passing through the origin, and third subspace is the whole space R2. Is this okay?
Okay, madam.
Yeah. So let's go to the next one. Here we have given one vector space V. V is the set of all functions from close to 0, 1 to real numbers such that f is continuous, and it is a vector space over the field R. And the vector addition is defined as the usual addition, that is f plus g of x is f of x plus g of x, and scalar multiplication is defined as c f of x equal to c into f of x. So if you want, you can just check the all condition of vector space whether it is satisfied or not. Anyhow, it is a vector space, and the question is which of the following is a subspace. So the first one, let us see A. A is set of all elements in V that satisfy the condition f of 0 equals 0. Is this a non-empty or not?
Yes, ma'am, it is non-empty. 0 is there.
Yeah. Because 0 is an element of A. What is the 0 element? 0 element means the function 0 function. 0 function, I am saying 0 is a function from close to 0, 1 to R. Okay. Close to 0, 1 to R is defined as 0x equal to x for all x in R. Since this is a constant function, it is a continuous function. So 0 is a element in the vector space V, and also 0, the value of the 0 function at 0 is 0. That means it satisfies this condition also. So this 0 function belongs to A. So that A is non-empty. A is a non-empty set. Now to check the condition, if f and g are in A, f plus g. What about f plus g? Okay, we need to say f plus g belongs to A. Okay, for f plus g belongs to A, what condition we should check? We need to prove this f plus g belongs to A. Yeah.
Closure, ma'am.
Like we have one theorem. If we already have A is a non-empty subset of our vector space V. For a non-empty subset to be a subspace of V, we just need to consider x plus y is also in A or xy in A, and Cx is also in A. So we are using that theorem, that is f plus g should belongs to A means f plus, so the condition of A is f of 0 should be 0. So f plus g of 0 should be 0. F plus g of 0 is f0 plus g0. Okay. Since f and g are in A, we know that f0 equals 0 and g0 equals 0. So this is also 0 plus 0, which is 0. Okay. So f plus g of 0 is 0. That means this function f plus g satisfies this condition. So we can say f plus g is also an element of A. Now next condition is CF. What is CF of 0? C times f of 0. C times f of 0 is 0, which is 0. That means CF is also belongs to A. Okay. So A is a non-empty set which satisfies both the condition of our theorem. So we can say A is a subspace. Now the second one is B. B means set of all elements in V, that is set of all functions in V with f of 0 equal to 0 and f of 1 equal to 0. Set of all f in V such that f0 equals 0, f of 1 equals 0. Okay. So what about this? Is this a subspace or not? Any guess? Is this a non-empty set? Just like the above case, we can say the 0 function belongs to B. Okay. So B is a non-empty set. Now what we want to see is Fg belongs to B. We need to prove that f plus g belongs to B. This is we need to check. Okay. For f plus g belongs to B, we need to verify two conditions. That is f plus g of 0 should be equal to 0 and f plus g of 1 also should be equal to 0. What is this f plus g of 0? This is f of 0 plus g of 0. Since f and g are elements of B, f0 is 0, g0 is 0. So this is 0. In the same way, f1 is 0, g1 is 0. That means this is also 0, f1 plus g1, which is equal 0. Okay. So f plus g satisfies, that is f plus g belongs to our B. Now what about CF? We need to say CF of 0 should be equal to 0 and okay, CF of 1 should be equal to 0. This is clear because this is C into f of 0 which is equal to C0 equal to 0. This is C into f of 1. This is very trivial to verify. This is also 0. So CF also belongs to B. Hence B is a subspace. So what we are getting is both the A and B are subspace. Okay. In this case, both the A and B are subspaces. Is the answer clear for everyone? Any doubt?
No, it's an constant function.
Which one?
F0 0 and F1 is 0, so it's a constant.
No, not constant function. The only thing we are saying is at 0 it is 0. It can be anything, like if I am saying f of x equal to x, okay, then we can say f of 0 equal to 0. right? That means F belongs to our set A. A is the set of all F in V such that F0 equal to 0. This F is not a constant function, right? In the same way, if I am
Yes, ma'am.
g of x equal to x into x minus 1. Here g is not a constant function, but g0 equal to 0 and g1 equal to 0. So this g belongs to our B. What is B? B is the set of all elements such that g0 should be equal to 0 and g1 equal to 0, right? This g satisfies both conditions, but g is not a constant function. This is not the set of all constant functions or not the set of all 0 functions, but the only thing is the value at 0 is 0 in this case, and the value at 0 is 0 and value at 1 is 0 in the second case. Is this okay?
Yes, ma'am.
Okay. So let us go to the next problem. Okay. Here we have given the space, vector space V equal to R3 over the field R, and the operation addition is given as the usual coordinate wise addition, and the multiplication is given as the usual coordinate wise multiplication. These two operations are given. So we know that V is a vector space, and we are given for subset. We need to check whether it is a subspace of or not. Okay, let us go to the first one. Yeah, what do you think, whether A is a subspace of R3 or not? Okay, whether A is a subspace. Okay, in order to check the subspace, the basic thing is the identity element. Here identity in R3 is 0 0 0. It should belongs to the subspace. Okay, this is a very basic thing we need to check. Is the 0 0 0 belongs to the first one A? Our A is set of all elements x, y, z in V. V is our R3 with two conditions satisfied. That means x plus 2y minus z equal to 1 and 2x minus y plus z equal to 2. That is, we need to find set of all x, y, z in R3 with these two conditions satisfied. Okay. This A, whether this 0 0 belongs to A or not, can anyone tell?
No, ma'am. No, ma'am.
No, because 0 0 0 does not satisfy this condition, because 0 plus 0 plus 0 minus 0 is not 1. So 0 0 0 does not belongs to A. Then is A can be a subspace? Of course no. If it is a subspace, it itself is a vector space. That means the additive identity should be there. Okay, so A is not a subspace. Now let us go to the second one. B is the set of all x, y, z such that x plus y plus z equals 0. So what do you think about B? Is this B a vector, or first of all, is this B contains our 0 element?
Yes.
Yes, because summation of 0 0 0 is 0. So this belongs to B. Now we got B is a non-empty set. Okay, B is a non-empty set. So we need to check whether if we are taking two elements from B, whether the sum is also in B, and also if we are taking the scalar multiplication, whether that is also in B. That is, I am taking two elements x1, y1, z1 and x2, y2, z2 in B. Okay, so okay, this belongs to B. What that means? X1, this condition is satisfied for these elements. X1 plus y1 plus z1 equal to 0, x2 plus y2 plus z2 equals 0. Now what we need to check is this sum should belongs to B or not. x1 y1 z1 plus x2 y2 z2. This is x1 plus x2, y1 plus y2, z1 plus z2. Okay, is this belongs to B or not?
Yes.
Yes, because the only thing we need to check is the sum of three coordinate is 0 or not. This is 0 because x1 plus x2 plus y1 plus y2 plus z1 plus z2. This we can write as like this, right? x1 plus y1 plus z1 plus x2 plus y2 plus z2, that is 0 plus 0. 0 plus 0 equals 0. Now, if I am taking any scalar and multiplying with an element x1, y1, z1, this is an element of B. So, what I am getting is Cx1 plus, Cx1, Cy1, Cz1. Is this belongs to B or not?
Yes, again.
Yes, again it belongs to B because the summation means C into x1 plus y1 plus z1, because this is 0, that is C into 0. Whatever the value of C, it will be 0. Okay. So, in both condition, the summation and the scalar multiplication belongs to B. That means B is a subspace. Now, let us go to the third one. Set of all x, y, z in B such that x, y equal z. Okay. Is this a subspace or not? What is your guess? Any guess? Okay.
No, ma'am.
No. Let us see one example for that. That means if I am taking two element 1 1 1, okay, this is a element of C because 1 into 1, that is x position into y position should be multiplying, this should be equal to the z position, 1 into 1 equal to 1. So, this is an element of C. So, if I am adding this 1 1 1 or if I am doing the scalar multiplication 2 times 1 1 1, what is this? 2 2 2. Is this belongs to C or not?
No, ma'am.
No, it does not belongs to C, right? Because x position into y position means 2 into 2, this is equal to 4, this is not equal to the z value 2, right? So, under the scalar multiplication, this set C is not closed. So, C is not a subspace. Now, let us move to the fourth one. Fourth one is set of all x, y, z such that x equals 1. So, what about this one? Is this a subspace or not? Is 0 0 0 belongs to D? What do you think?
No, ma'am. X would be equals to 1 always.
Yeah, x is always 1. So, this element will not belongs to D. That means our basic element, identity element is not in D, right? So, D cannot be a subspace. D is not a subspace. Okay. Is all the 4 options clear for everyone? If you have any doubt, you can ask. Anyone is having doubt? Okay, otherwise let us move to the next problem. Here the question is, if Pnx denotes the vector space of all polynomials of degree less than or equal to n over r. That is Pnx we can write it as a0 plus a1x plus a2x square plus etc. plus an minus 1 x power n minus 1 plus an x power n with ai belongs to r. Okay, that is, this is the vector space over R. So we are taking the coefficient over R. So this is our Pnx, that means set of all polynomials of degree. Even though I am writing this up to degree n, if I am taking an equal to 0, I will get degree up to n minus 1, right? So this is what this means, that is degree less than or equal to n. So I can take any polynomial of degree less than or equal to n in this combination. So I am writing the Pnx as the set of all these elements. Okay. So the question is dimension of Pn of x. This is our question. So we need to find a basis for Pnx. So if I am seeing a1, a2, etc., suppose a1, a2, etc. up to an, all these are 0 and a0 is a non-zero element. That means we have a polynomial f of x equal to a0, that is a constant polynomial. So can you tell about any or any element which generates the constant polynomial? That is a constant, like if we are having one constant polynomial, we need a basic element which spans the constant polynomial. Can you think about such an element?
1.
1, yeah. So I am taking 1, first element as 1, because 1 spans all the constants here in the Pn of x. If we are having a1, a2, etc., an are all 0, we are having constant polynomial and we are taking 1 as the generator for the constant polynomial. Now I am taking a2, etc., up from a2 to an, all are 0. That means f of x is a0 plus a1x, with a0 and a1 are non-zero. That is a polynomial of degree 1. Of course, this f of x is also in Pn of x. So here this a0 we can generate by this 1. That means this we can write it as a0 into 1 plus this I am writing it as a1 into x. That means we are generating this polynomial with this 1 and x. So 1 already in our basis. Now I am adding this x also. Okay. So we got 2 elements in our basis, 1 and x. These 2 elements will generate these 2. This constant element will be generated by this element and this first degree polynomial will also be generated by this element. Okay. Now I am taking the second degree polynomial, a0 plus a1x plus a2x square. So in order to generate these elements, which one I should add in the basis? X square, right? So this term is already generated by the constant term, this is generated by the x term and this is generated by x square. So in the same way, if I am having an nth degree polynomial, I am taking up to nth degree. This is our maximum polynomial. So what will be the last element here? X power n. Yeah. So up to, like if we are taking 1 x square etc. x power n, we can say any polynomial is generated by, that is if I am taking any polynomial a0 plus a1x plus etc. an x power n, it is generated by 1 x square etc. x power n, because I am writing this as a0 into 1 plus a1 into x plus etc. plus an into x power n. That is a linear combination of 1 x etc. x power n. So we got span of B equals our Pn of x. Okay. We got one set which spans the polynomial, set of all polynomials. Now we need to check whether this is linearly independent or not. If it is linearly independent, we can say this B is a basis. If it is linearly dependent, we cannot say it is a basis. So, we will check is B linearly independent. Suppose for that what we will take is a linear combination. Suppose we are taking a linear combination of these elements, that is C1 into 1 plus C2 x plus, otherwise let me take C0 into 1 plus C1 x plus C2 x square plus etc. Cn x power n. So, I am taking the linear combination and I am equating it to the 0. What is the 0 here? This is the 0 polynomial. 0 polynomial. Okay. So, in order to say this B is linearly independent, we need to say each of the C0, C1, etc., Cn are all 0. Okay. Now, let me take f of x equals C0 plus C1 x plus etc. plus Cn x power n, and we know that this is the 0 element. What is this means? This means 0 means 0x equals 0 for all x in R. Okay. So, if I am taking any x in R, I can say this C0 plus C1 etc. Cn x power n is 0. That implies any x in R is a root of root or 0. That is, any x in R is a solution for the function f of x. Okay, is this clear? So, we get any x in R is a solution of f of x. But what is this f of x? F of x is a nth degree polynomial. Maximum degree is n. Nth degree polynomial. So, what is the maximum possible zeros of n? Yeah. Sorry, zeros of that is f is an nth degree polynomial. So, we know that by fundamental theorem n can have at most f can have at most n zeros, but what we are saying is this is having all x is a 0. That means all elements in that is infinite number of zeros are for this function f of x. So, f of x is having infinite number of 0 means f of x is trivially a 0 function. That means trivially a 0 function means all C0, C1 are should be non 0. That is, Ci should be equal to 0. That means if at least at least one Ci is not 0, then we will have one correspondingly we will have one x power I there. This can have at most n zeros, sorry, I zeros, right. So, in order for this condition to be satisfied, all the Ci should be 0. Is the argument clear? Anyone is having doubt, or should I explain again? Is this clear? Can you repeat?
No, ma'am, not clear.
Not clear, okay. See, our function is f of x. We are equating this f of x to 0. Okay, f of x to 0 means this f of x is a 0 function. What that means is f of 0, okay, let me write it. What we are having is f of x equals C0 plus
பிகர் நம்பர் மேல போட்டுருக்காங்க. மேல என்ன போட்டுருக்காங்க? 74. கீழ என்ன போட்டுருக்காங்க? 30 தான் போட்டுருக்காங்க.
Yeah.
74 34.
Can you mute yourself? Someone is speaking. Please mute. So this is our function, and we are equating this to 0. That means 0 function, 0 polynomial. That means f of 0 equal to 0. Sorry. F of x equal to 0 for all x in R. Okay. Suppose f is a suppose at least one CA is non-zero. That means I am writing f of C0 plus C1 x plus etc. Ci x power I. C0, C1 up to Ci minus 1, it can be 0, non-zero, whatever. The only thing I am having is this Ci is non-zero. So this f of x will have only maximum, only possible number is only possible number of 0, I, because it is an ith degree polynomial, right? Ith degree polynomial can have at most I zeros. Okay, but we know that this f of x is having infinite number of zeros. This is a contradiction. Are you getting the contradiction now?
Oh, yes, ma'am.
Yeah, this is because we assume that at least one CA is non-zero. This is why we are getting the contradiction. Okay, so the only possible thing is CA should be equal to 0 for all I. Is this clear now?
Yes, ma'am. Proceed.
Yeah, okay. Any other is having doubt? Any other doubts?
புரியல.
Anyone is having doubt? Yeah, if you have any doubt you can ask, otherwise let us wind up the session. It's already 7 o'clock. Has someone raised a hand? Are you having any doubt?
Oh, ma'am, previous slide, last slide.
Yeah. Yeah, what's your doubt?
Done, ma'am.
Okay, is this clear? Is everything clear for everyone? Okay, if it is clear or if you have no doubt, you can leave the meeting. Okay, last portion, can you?
Ma'am, tomorrow also the session will be there.
Yeah, tomorrow at 7 o'clock, I think. Yeah.
Then if the degree of polynomial is less than n, then it is not equal to n, but it is less than.
Yeah, it is not equal to n, less than or equal to n. If it is equal to n, then it is not a vector space actually.
If it is less than n, then also same thing happen.
Yeah, we are dealing with the case set of all polynomials where degree is less than or equal to n.
No, but if the case is the polynomial of degree less than n, not equal to n.
No,
only less than n.
No, less than or equal to n. Okay, you are asking when the case is less than
I
n.
am asking
Yeah,
if it is less than n,
then is this a vector space? Okay. Yeah, then also it will be a vector space, and less than n means the degree is less than or equal to n minus 1, right? That means in this case we got the dimension, okay, that I didn't mention. Here dimension is dimension of Pn of x is n plus 1. Okay, if the
Here
degree,
it is n plus 1.
yeah, here
it is n plus 1.
yeah,
But if it is less than n, then
if it is less than n, that means that is Pn minus 1 of x, means
yeah.
set of all polynomial of degree strictly less than n. Strictly less than n means less, this is same as less than or equal to n minus 1, right?
No. Yes.
Right. So the case is just the one case below. Here in the case what we will get is the basis will be 1x etc. x power n minus 1. Okay.
Yeah.
This is the only difference. We are just going one step backwards.
So dimension will be n minus 1 plus 1. It is
In
n.
this case, dimension of Pn minus 1x, that is, if it is strictly less than n, this will be n.
So it is n.
Yeah, in this case.
Okay.
Yeah.
Ma'am,
Yeah.
it will be a proper vector space here.
Which one? This Pn minus 1x.
When the dimension is less than n.
Yeah, proper subspace. Are you asking? This Pn minus 1 is a proper subspace of Pn of x. Is this the question?
Yeah.
Yeah. Any other doubt? Okay, I think no more doubts. So if you are not having doubt, you can leave, or okay, let me stop the today's session. We will meet on the next Monday, same time. Yeah, thank you everyone for attending. Yeah,
Thank you very much for your patience in answering the questions.
Yeah, thank you all.